Hello everyone and welcome to this interesting session on TensorFlow Image Classification. Now deep learning and TensorFlow are one of the hottest topics nowadays, and for a good reason. The advancement in this industry has made it possible for machines and computers to perform such features which are not capable for humans to do at all. And artificial intelligence is going to create 2.3 million jobs by 2020, and a lot of this is being made possible by TensorFlow. So guys, in this session, first of all, I'll brief you about TensorFlow, and moving forward, we'll see some of the applications of TensorFlow. After that, I'll brief you about image recognition, what is it and how is it being implemented. And after that, we'll straight away jump to our use case for TensorFlow image classification. So what exactly is TensorFlow? Now, TensorFlow is Google's open source machine learning framework for data flow programming across a range of tasks. Now, if we talk about data flow programming, that involves graphs. So the nodes in the graph represent the mathematical operation, while the graph edges represent the multidimensional data arrays, which are also known as tensors. So tensors are nothing but just the multidimensional arrays and extension to the two-dimensional table to data with a higher dimension. There are many features of TensorFlow which makes it appropriate for deep learning, as it is the core open source library which helps you develop and train machine learning models. Now, a major advantage of using TensorFlow is that it makes image-related processes easier. For example, if we take Airbnb, the leading global online marketplace and hospitality service company, it improves the guest experience by using TensorFlow to classify images and detect objects at scale. So what it does is that takes an image as input and automatically classifies it as a bedroom or a washroom or the hall or the balcony. Now, if we talk about healthcare industry, GE Healthcare trained a neural network using TensorFlow to identify specific anatomy during the brain MRI exams to help improve the speed and the reliability. Not only this, TensorFlow is being used in the industry for a lot of other purposes. But today our focus is on image classification. Which brings the question, what exactly is image classification? Now, the intent of image classification or classification in general is to categorize all the pixels in a digital image into one or several land cover classes or themes basically. Now, this categorized data may be used to produce thematic maps of the land cover present in an image. And it also refers to the task of extracting information classes from a multiband raster image. Now, the resulting raster from image classification can be used to create thematic maps. And depending on the interaction between the analyst and the computer during classification, there are two types of classification basically, which are the supervised and the unsupervised. So the first example of what we're going to do is train a neural network model to classify images of clothing, like sneakers and shirts. So here I'm using Keras, which is a high-level API to build and train models in TensorFlow. It is also used for fast prototyping, advanced research, and production, with three key advantages. First of all, it is user-friendly. So Keras has a simple, consistent interface optimized for common use cases. It provides clear and actionable feedback for user errors. Next, we have modular and composable. Keras models are made by connecting configurable building blocks together with few restrictions. And the third advantage is easy to extend. Now, we can write custom building blocks to express new ideas for research. You can create new layers, loss functions, and develop state-of-the-art models. So first of all, what we're going to do is import the Fashion MNIST dataset. So we are going to use the Fashion MNIST dataset, which contains 70,000 grayscale images in 10 categories. Now the images show individual articles of clothing at low resolution, which is 28 by 28 pixels, as you can see here. Now what we'll do, we'll use 60,000 images to train the network, and the rest 10,000 images we'll use to evaluate how accurately the network learned to classify the images. Now what you can do is access the Fashion MNIST directly from TensorFlow. Just import and load the data. So what I'm going to do is create an IPython notebook here. So I'm going to name it as image classification fashion MNIST. So first of all, to load the data, what we're going to do is we're going to import TensorFlow and import Keras. So we're going to import TensorFlow as TF. From TensorFlow, we're going to import Keras. And we're going to import some helper libraries such as NumPy and Matplotlib. And to check the version of TensorFlow, here we have 1.9. So next what we are going to do is load the data. So as you can see here, we are using the keras.dataset.fashion MNIST because it's already there in Keras. And loading the dataset returns 4 NumPy arrays. Now the train images and the train labels arrays are the training dataset, and these are the data which the model uses to learn. The model is tested against the test set, which are the test images and the test label arrays. Now the images are 28 by 28 NumPy arrays with pixel values ranging between 0 to 255. Now the labels are an array of integers ranging from 0 to 9, and these correspond to the class of clothing the image represents. Now each image is mapped to a single label. Since the class names are not included with the dataset, we have to store them here to use later while plotting the images. So what we're going to do is define the class names. So we have t-shirt, top, trouser, pullover, dresses, coat, sandals, shirt, your sneaker, bag, and ankle boot. So after we loaded the data, let's explore the data format or the data set before training the model. So as you can see from the following code, it shows that we have 60,000 images in the training set, with each image represented at 28 by 28 pixels. Likewise, there are 60,000 labels in the training data set. And if we talk about the label, it is an integer between 0 to 9. So as you can see here, it's an array starting from 9, which is 0, 0, 3, 0, 5. And there are 10,000 images in the test set. Each of the image is represented as a 28 cross 28 pixel. And there are 10,000 images labeled. So before processing, what we need to do is pre-process the data. Now, if you inspect the first image in the training set, you will see that the image pixel values fall in the range of 0 to 255. Now we scale these values to range of 0 to 1, and before feeding to the neural network model, for this we divide the values by 255. So it's important that the training set and the testing set are pre-processed in the same way. That's really important. Now what we are going to do is to display the first 25 images from the training set and display the class's name below each image. And what we'll do is verify if the data is in the correct format, and after that we are ready to build and train the network. So let me just display the images. And now comes building the model. So building the neural network requires configuring the layers of the model and then compiling the model. So let's set up the layers first. Now the basic building block of a neural network is a layer. Layers extract representations from the data fed into them, and hopefully these representations are more meaningful for the problem at hand. Now most of the deep learning consists of chaining together simple layers. Most layers like the tf.keras.layers.tens have parameters that are learned during the training. So as you can see here, we have our model, which is keras.sequential, and we are using the flatten and the dense layers. So as you can see, the input shape is 28 cross 28. So the first layer in this network, which is the tf.keras.layers.flatten, it transforms the format of the images from a 2D array of 28 by 28 to a 1D array of 28 cross 28, which is 784 pixels. Think of this layer as unstacking rows of pixels in the image and lining them up. Now this layer has no parameters to learn, it only reformats the data. Now after the pixels are flattened, the network consists of a sequence of 2 dense layers. Now these are densely connected or fully connected neural layers. So the first dense layer has 128 nodes, or basically 128 neurons, while the second or the last layer has 10 nodes with SoftMax layer, and this returns an array of 10 probability scores that sum to 1. Now each node contains a score that indicates the probability that the current image belongs to one of those 10 classes. So next what we're going to do is compile the model. So before the model is ready for training, it needs few more settings. Now these are added during the model's compile step. So for example, we have the loss function, which measures how accurate the model is during the training, and we want to minimize the function to steer the model in the right direction. Another important aspect is the optimizer. So this is how the model is updated based on the data it sees and its loss function. And finally, we have the metrics, which are used to monitor the training and testing steps. And the following example uses accuracy, which is the fraction of the images that are correctly classified. So guys, now we're going to train the model. So training the neural network model requires some steps. The first one is feeding the training data to the model. And in this example, it is the train underscore images and the train underscore label arrays. And after that, the model learns to associate the images and labels. And after that, we ask the model to make predictions about a test set. And in this example, which is the test underscore images array. And what we do is we verify that the prediction match the labels from the test underscore label array. To start the training, what we're going to do is call the model.fit method, and the model is fit to the training data. So as you can see here, we are doing model.fit, and in that we have given the train underscore images, the train labels, and the epochs we have mentioned is at 5. So instead of 5, I'm going to train it for 10 epochs to see whether there are any changes, because I've already run this model once with 5 epochs. So as the model trains, the loss and the accuracy metrics are displayed here. So as you can see here, the first epoch, the loss is 0.5, whereas the accuracy is 0.82. And coming down to our 10th epoch, as you can see here, the loss is 0.24, all the way reduced from 0.5, and the accuracy has increased from 82% to 91%. Now, next what we're going to do is evaluate the accuracy. So now we're going to compare how the model performs on the test data set. So as you can see here, the test accuracy is 0.88, that is 84%. Now it turns out that the accuracy on the test is a little less than the accuracy on the training data set. Now this gap between the training accuracy and the testing accuracy is an example of overfitting. So overfitting is when a machine learning model performs worse on a new data than on the training data. So what we're going to do is now make predictions. So with the model trained, we can use it to make prediction about some images. So what we're going to do is prediction equals model.predict, and we're going to use the test underscore images. So here the model has predicted the label for each image in the testing set. So let's take a look at the first prediction. So as you can see here, a prediction is an array of 10 numbers. Now these describe the confidence of the model that the image corresponds to each of the 10 different articles of clothing. So we can see which label has the highest confidence value. So as you can see, the output here we are getting is 9. So the model is most confident that the image is an ankle boot, or the class number 9. So let's see and check if the test label sees this as the correct output. So as you can see here, the test label is also 9. Now we can graph this to look at the full set of 10 channels. So as you can see here, we have defined the plot image and we have defined the plot value array. So let's look at the 0th image prediction and the prediction array first. So as you can see here, we have the ankle boot, which is classified 100%. And if we have a look at the 12th image here, as you can see here, first let's have a look at the 15th image. And now having a look at the 10th image, we can see here the code is 90% code, but it's also defined as some other category. Now let us plot several images with the predictions, and the correct prediction labels are green and the incorrect prediction labels are red here. So the number gives the current percentage out of 100 for the predicted label, and note that it can be wrong even if we are very, very confident. So as you can see here, a lot of these images are 100% correct, but sometimes, as you can see here, the sneaker is classified as a sandal, but it's actually a sneaker. It's identified as an 88% sandal. So that's a very incorrect prediction. as well as if we have a look at the code, which is 77% code, it has classified it as other elements. Now finally, what we're going to do is use the trained model to make a prediction about a single image. So let's check first. Let's grab the image from the data set. So what we're going to do is img equals npexpand. We get the dimensions. So as you can see here, it's 28, 28. The tf.keras model are optimized to make predictions on a batch or a collection of examples at once. So even though we are using a single image, we need to add it to the list. As you can see here, we are adding the image to the batch where it's the only member. So now what we're going to do is predict the image. And as you can see here, the model.predict returns a list of lists, one of each image in the batch of the data. Now let's grab the predictions for our only image in the batch. So as you can see here, as before, the model projects a label of 9, which is the angle boot. So guys, this was an easy example on how to classify images creating a small neural network of, this was just 3 layers, but the image sizes are small, it's 28 by 28 pixels, and it is comparatively easier to classify these images. Now what I'm going to do next is classify images from the CIFAR10 dataset. Now the dataset consists of airplanes, dogs, cats, and other objects. We'll pre-process the images, then train a convolutional neural network on all the samples. So guys, convolutional neural network here is the tricky part of this example, and the images need to be normalized and the labels need to be one-hot encoded. The first code block here, what I'm going to do is to download the CIFAR10 dataset. So guys, I'm not going to execute it as I've already downloaded the CIFAR10 dataset and untied it. So this is for people who have not downloaded the dataset and are executing this practical for the first time. So before we jump in, there are some references to look up, such as Python Pickle, what we are going to work on. So what it does is implements binary protocols for serializing and deserializing a Python object structure. We have numpy.reshape and numpy.transpose as we did earlier. We reshaped it, but we're going to use it again, numpy.reshape and transpose. We're going to use the TensorFlow convolution 2D, and we're going to use the numpy transpose with a list of access explanation. So what we're going to do is import pickle, numpy, and matplotlib. Now the important part here is first of all understanding the data. So the original batch or the batch data is 10,000 into 3072 dimensional tensor expressed in a numpy array, where the number of columns, which is 10,000, indicates the number of sample data as stated in the CIFAR10 dataset. Now the row vector 3072 represents an color image of 32 cross 32 pixels. And since this project is going to use convolutional neural network for the classification task, the row vector 3072 is not an appropriate form of image data to feed. In order to feed an image data into a CNN model, the dimension of the tensor representing an image data should be either width into height into the number of channel or number of channel into width into height. Now it depends on your choice. In this particular project, I'm going to use the dimensions of the first choice because the default choice in TensorFlow CNN operation is so. Now let's understand the original labels of the data. So the label data is just a list of 10,000 numbers in the range 0 to 9, which corresponds to each of the 10 classes in CIFAR10 dataset, which are basically the airplane, we have the automobile, we have bird, cat, deer, dog, frog, horse, ship, and truck. Now what we need to do is modify into a new shape. So what we're going to do is define a label name with all the labels. So how do we reshape the data into such a form? So the row vector 3072 has the exact same number of elements if we calculate 32 into 32 into 3. Now 32 into 32 is the dimension of the image. So in order to reshape the row vector, there are 2 steps required. First of all, what we're going to do is divide the row vector into 3 pieces. Each pieces correspond to each channel. So this results in 3 into 1024 dimension of tensor. And next what I'm going to do is divide the resulting tensor from the previous step with 32. So 32 here means the width of an image. And this results in 3 cross 32 cross 32. Now, in order to implement the directions written in logical sense in NumPy, the reshape function should be called in the following arguments. And this is not the end of the story. Now the image data is represented as number of channels into width into height form. However, this is not the reshape TensorFlow and Matplotlib are expecting. What they are expecting is a different shape, which is of width into height into number of channels instead. So what we're going to do is swap the order of each of these axes. And that is where the transpose function comes into picture. So the transpose function can take a list of axes. Each of the values specifies where it wants to move around. And that is how you reshape. So let's explore the data. So understanding a data is a part of making predictions on the data. Playing around with the code cell by changing the batch ID and sample ID. So as you can see here, we have the display stats. So the display stats, what I have defined here, answers some of the questions like, in a given batch of data, what are all the possible labels? What is the range of values for the image data? And are the labels in the order or random? Now, if we look at stats of batch 3 here, so when we explore the dataset, given the batch ID 3, sample ID 7000. So as you can see here, the number of airplanes are 994. We have automobile, which is 1042. And as you can see here, the image here is given of an airplane. And the image shape is 32 cross 32 cross 3, which again is width into height into the number of channels. Now that we have loaded the data, what we have to do is pre-process it. So what we're going to do is normalize it, and for that we are going to use the min-max normalization. Here we have defined normalize function, and after that what we are going to do is do the one-hot encode. Since the output of our model is going to show the probabilities of where an image should be categorized as a prediction, there should be a vector having the same number of elements as the number of image classes. For instance, the CIFAR 10 provides 10 different classes of image, so we need a vector in the size 10 as well. Each element represents the predicting probability of each class. Also, our model should be able to compare the prediction with the ground truth label. It means that the shape of the label data should also be transformed into the vector size of 10. So one hot encode function takes the input x, which is the list of labels, and the total number of elements in the list is the total number of samples in a batch. So what this function will return is a two-dimensional tensor where the number of row is the size of the batch and the number of column is the number of image classes. And what we're going to do is pre-process all the data and save it. So this code here uses the previously implemented function, the normalize and the one-hot encode to pre-process the given data set, and running the code will help pre-process all the CIFAR 10 data and save it to the file. Now it also uses 10% of training data for validation purposes. So as you can see here, we are pre-processing it. We have the normalize one-hot encode, saving the new file. We are also loading the test data set and pre-processing and saving all the test data set at once. So next what we are going to do is build our TensorFlow network. So it's a convolutional layer and fully connected layer. So first of all, what we're going to do is remove the previous weights and biases if there are any. And we're going to provide an input which is x, which is going to be an tensor of 32 cross 32 cross 3, which is the input underscore x, and y will be the output, which is output underscore y. Now the entire model which I'm going to create here consists of 14 layers in total. So in addition to the layers listed, we're going to have to specify the techniques which are applied to build the model. So the first layer is a convolutional with 64 different filters of the size 3 cross 3. Then we have max pooling by 2. Then again we have convolution with 128. Then we have max pooling by 2. Then again convolution with 256. And so on. Our convolution increases till the 8th layer, which is the max pooling by 2. And after that we are going to flattening the 3D output of the last convolutional option. Then we have the fully connected layers with 128 units. We're going to use dropout and we're going to use the batch normalization. Again, we have 2-3 layers of fully connected layers, and the final layer is the fully connected layer with 10 units. Now these 10 units represent the 10 classes of the images here. This image describes how the conceptual convolving operation differs from the TensorFlow implementation when you use the channel into width into height tensor format. Now next what we are going to do is define our hyperparameters. So as you can see here, we have epochs, which are the number of iterations. We have the batch size, which is the highest number that the machine has memory for, and most people set them to the common size of memory. Then we have the keep underscore probability, which is the probability of keeping a node using dropout, and we have the learning rate, which is the number how fast the model learns. So the epochs here, I'm going to keep it as 5. The batch size is 128 and the probability is 0.7, whereas the learning rate I'm keeping it to 0.001. Next, what we are going to do is define our cost function and optimizer. So as you can see here, we are using the tf.reduce_mean, and inside that we are using the SoftMax cross entropy with logits. And for accuracy, we are going to use the tf.argmax, and what we're going to do is minimize the cost, and we are going to use the Adam optimizer for this purpose. Now, next what we need to do is that we have defined the cost, the optimizer, and the accuracy. What we are going to do is train the neural network. If we define our training a neural network, so we have the session, we have the optimizer, the probability, feature batch, and the label batch. And this is how we do a single optimization. Now for showing the stats, what we have here is print stats. It will print the validation accuracy and also the loss. Here we have the fully trained model. So what we're going to do is split the features and the labels into batches. And after that, we're going to load the pre-processed training data and return them in batches of the batch size or less. Now to save the model, we need to provide the model path. What we're going to do is initialize the variables with the ses.run, and then we have our training cycles, which is for epoch and range of epochs. We're going to loop it over all the batches, and then finally, once the training is done, what we're going to do is save the model. So we're going to use tf.train.saver and save it to the defined path. Now, as you can see here, once the training has started, now this training will take around 2 or 3 hours depending upon your capacity or upon your CPU. So my system has 16 GB RAM, so even in spite of the 16 GB RAM, it took around 2 to 3 hours. So I also executed this practical once before, so let me just show you. So as you can see here, we have reached epoch 1, epoch 2, and epoch 3 now, but if we have a look at the example I executed earlier, so as you can see here, during the 10 epochs, first of all, as you can see, the loss started from 2.1 and the accuracy was 0.21. Coming to the 10th epoch of batch 5, since each epoch has 5 batches, it will take a lot of time, and the data is so huge that it will take some time, unless and until you have a supercomputer which does all the computing in just fraction of seconds. So after the 10th epoch and batch 5, we can see the loss has been decreased to 0.01 from 2.11. That's a very good achievement, but the accuracy is still at 75%. This value can change if you train your model for long, but do not train for much longer purposes because it might result in overfitting or underfitting, as a matter of fact. Now the model has been saved to the disk, and what we need to do is test the model. So for that, what we are going to do is split the features and the label into batches again, and then we are going to use the SoftMax predictions. We're going to input the path of the model, and we're going to get the tensors from the loaded model, get the accuracy in batches for memory limitations, and then again we'll print the random samples. So as you can see here, the testing accuracy what we got is 0.58. Now this can change if we train the model again and use another set of images. So the SoftMax prediction what we got here were the truck, the automobile, frog, airplane, and also the frog. So as you can see here, the truck, it was classified as horse, a ship, and an airplane, but not a truck. The automobile was classified as automobile, but is also classified as ship and a dog. Now this value will change when you train your data with more and more epochs, and a good learning rate. Learning rate was not the issue, but the number of epochs were very less, so we have to train it for a large number of epochs since we do not have that much time. If you guys need the code, please mention it in the comments section below so that we can revert it to you via email. And you can play with the code. Then again, you can change the number of epochs, you can change the batch size, play with it and see how long does it take to get a better accuracy. So as you can see here, we have 2 frogs, out of which a frog was classified as a deer, bird, and a dog. And as you can see here, the frog was classified as a dog as well. Now guys, that is it for, I hope you got to know about the classification, image classification, how it works, how we can use a 3-layer neural network and get the classification done. Just now I showed you the fashion MNIST dataset, how we can perform it, the classification on it, and it was easy. But as the dimension increase and the image size also increases, it is difficult. So what you need to do is there are a lot of pre-trained models available on TensorFlow's GitHub repository. You can choose any of the pre-trained models, and all of these models have some or other advantage over the others. What I mean to say is that some models might perform faster, some models might perform slower but give you a better accuracy. So it depends upon the model you choose or the model you create or build, how fast it is going to learn, how slow it is going to learn, how much accuracy it's going to provide. So that all depends on you as well. So guys, if you have any queries regarding this session, please feel free to mention it in the comments section below. And if you have any queries regarding the code, please feel free to mention it. We'll get back to you as soon as possible. Till then, thank you and happy learning.